Okay, so the last example we'll look at is the marble rolling around in a bowl. So we need a circular or semicircular shaped bowl for the marble to roll around in. And put the marble over here to the side. So first let's take a look at the forces acting on this marble. And obviously we're talking about the amplitude of the marble rolling back and forth in the bowl. The displacement is along a curve. We're going to see that this problem is essentially the exact same problem as the pendulum, just with a little labeling difference. One thing that's not going to change, though, is that there is a force, which is the weight, mg, and in this case there is a normal force, and that normal force points towards the center of the bowl. Remember, the bowl is circular. This would refer specifically to bowls with a perfectly circular shape. If it has an elliptical shape or some other shape, then it would change things a little bit. So we're not going to worry about that too much. We'll keep it in the perfectly circular bowl, and this is a situation of stable equilibrium, because anytime you move the marble to one side, it puts a restoring force. That is to say that if I move it to the right, the restoring force is to the left. If I move it to the left, the restoring force is to the right. However, what we're going to do is we're going to get rid of this weight arrow, and we're going to replace it with two different arrows. The first is the radial component of the weight. Now, let me point out that just like it was for the pendulum, this angle between the location of the marble relative to the center of the bowl and the line which is drawn directly down is the same as this angle, for the same reasons. We have two parallel lines, I should say, with a transversal cutting them. So this is the component which is adjacent to that angle. That means that I could determine that component by using the cosine, mg cosine. That one's not going to be very interesting, but this one will be a little more useful, and this is the tangential component, and that's mg sine theta. Okay, so now at this point we don't need this, so we have essentially three forces: the normal force, mg cosine theta, the weight, the radial portion of the weight, and the tangential portion of the weight. So let's just take a look real quickly at the two net force equations. In the radial direction, what we have is the marble is neither moving inward towards the center of the bowl, nor is it moving outward from the center of the bowl. So in all cases, these two forces must add up to the same thing in a way that would mean that we would end up with no net force acting on these. And that's going to be true no matter where the marble is within it. So that's not particularly interesting. All it tells us is that you can find the value of the normal force by calculating mg times the cosine of theta. You'll find it greatest at the bottom, and you'll find that it's least when it's up here perfectly parallel with the center of the bowl. The more important equation is the tangential direction, because there's only one force. There is no counterpart to the opposite direction. So therefore there will be an acceleration. There's no possible way you could have a single force and not have acceleration, because the only way would be if this force was zero, which in this case it is clearly not. It is a restoring force, so that means that the force acts in the direction opposite to the direction of its motion. So if we, for example, look at where this is right now, this is to the right in the positive direction. That means that the force is in the negative direction. In any case, the net force will always be in the direction which is opposite to whatever direction it's accelerating. So when it's to the right, it's accelerating to the left. When it's to the left, the acceleration is to the right. And right away you can see that, just like we saw with the pendulum, the mass is not relevant. It does not matter what the mass of the marble is. Any marble, regardless of its mass, would have the exact same simple harmonic motion. What will affect it is obviously gravity, and we're going to make the same kind of motion that we made with the pendulum in terms of eliminating that sine feature, because technically, as this is right now, this is not simple harmonic motion. It is harmonic motion, but it's not simple harmonic motion, and we would like to simplify this just a little bit. So the first thing that we're going to do is to recognize that the radius r is related to the displacement through the formula x is equal to r theta. The displacement is equal, the arc length, x, is equal to the radius times the angle in radians. That means that theta is equal to x over r. Just like we saw in the pendulum, the only difference is, essentially the only difference in this problem is that where this in the pendulum was labeled as L, the length of the string, we're calling it r, but we could have just as easily in the pendulum problem referred to that as r. It's essentially the exact same problem. The one difference in the forces is that this is called the normal force as opposed to the tension, but again, we're really not concerned with this equation at all, so it really has no bearing on the simple harmonic motion of the object. What that's going to allow us to do is to replace theta with this statement x over r, and then making the same move that we made in the pendulum problem, we'll use the small angle approximation. So obviously in this case it would not be acceptable to allow the marble to roll quite as far as I've allowed it to roll, because this is probably 40 degrees or more. So typically what we're going to be talking about is the marble rolling back and forth down at the bottom, just like the way a pendulum on a grandfather clock might work. Very small oscillations, let's say usually less than 10 degrees, but generally speaking even up to 20 degrees. The small angle approximation is going to give you a pretty reasonable answer. So by using the small angle approximation, what I'll be able to do is to eliminate the sign. Remember, the small angle approximation is that x over r is approximately equal to the sine of x over r. That is to say, the angle is approximately equal to the value of the angle. It's the sine of the angle. So that's going to give us a new statement that a is equal to minus g, and I'll replace sine of x over r with simply x over r. And since the r is a constant, I mean the radius of the bowl certainly cannot change during the course of the motion. Gravity is very unlikely to change during the course of the motion. And so that gives us a is equal to minus g over r. These are the constants of this particular physical situation, x. And once again, this is exactly the equation of simple harmonic motion. So let's put over here to the side, omega squared in that case must then be equal to g over r, or omega is equal to the square root of g divided by r. For the period, that's 2 pi over omega, so t must be equal to 2 pi, and since omega is on the bottom, we'll flip that, r over g. So let me bring back the notes from the pendulum. So if you remember, we found that for the pendulum that omega was equal to square root of g over L, and that for the period it was 2 pi L over g. Essentially these are the exact same equations. The only difference is that we replaced L with the label R, but they are effectively the same thing because the length of the pendulum is the same as the radius. This length here is playing the role of the radius here because it's the distance from the center to the outward circle of its motion. Same thing for the pendulum. The circular portion of its motion is going to be from the center where it's connected out to where the length of the string is. And so effectively the pendulum and the marble and the bowl problem are the same thing. It's just a little bit of labeling, and so I won't do any examples for that one because they would look exactly the same as the pendulum.